Good day, everyone. Today we will be discussing the chemistry of the environment. What is it? Environmental chemistry studies how chemicals and biochemical processes interact with the environment and affect ecosystems. Its goal is to promote sustainability, conserve resources, and protect the environment. Success in this field requires strong analytical skills, sound judgment, and problem solving abilities. Earth's atmosphere. Atmospheric chemistry studies the composition of the atmosphere and the interactions of gases, liquids, and solids with the air, Earth's surface, and organisms, including the effects of human activities. The atmosphere is divided into four layers based on temperature changes to simplify the study and understand processes within each layer. The four layers, according to the variation of the temperature, are ionosphere or aurora or thermosphere, mesosphere, stratosphere, and troposphere. About 100 kilometer, the thermosphere and ionosphere have rising temperatures and mainly consist of hydrogen and helium atoms, with the ionosphere playing a key role in space exploration. Below the mesosphere, or 50 to 100 kilometers, has decreasing temperatures and contains molecules like oxygen, ozone, and nitric oxide, crucial for understanding Earth's environment and space science. The stratosphere, 10 to 50 kilometers, has rising temperatures and an ozone layer that absorbs UV radiation, while the troposphere below it is where weather occurs, with the atmosphere composed mainly of nitrogen, oxygen, and argon, crucial for climate, weather, and protection from solar radiation. What gases are pollutants in the atmosphere? In atmospheric science, understanding human generated gases like carbon dioxide or CO2, or carbon monoxide or CO, or ozone O3, and nitrogen oxides or NOx is crucial as they contribute to climate change, air pollution, and environmental damage. Methane or CH4, sulfur oxides or SOx, chlorofluorocarbons or CFCs, and water vapor H2O are key pollutants that contribute to global warming or acid rain, ozone depletion, and weather phenomena, impacting air quality, human health, and ecosystems. Human activities like burning fuels, deforestation, and livestock farming release large amounts of greenhouse gases or CO2, CH4, N2O, intensifying the natural greenhouse effect. This traps more heat, accelerates global warming, and disrupts ecosystems, weather patterns, and global climate stability. The decade from 2011 to 2020 was the warmest on record, with human-driven global warming increasing to at zero point 0.2 Celsius per decade. And a 2 Celsius rise would cause severe impacts. Efforts are focused on limiting warming to below 2 Celsius, ideally 1.5 Celsius to protect ecosystems and health.
The greenhouse effect, driven by gases like CO2, CH4, N2O, and fluorinated gases from human activities, is the primary cause of climate change, significantly contributing to global warming. Carbon dioxide is the leading human-driven contributor to global warming, with levels rising 48% above pre-industrial levels by 2020, while methane, nitrous oxide, and non-greenhouse pollutants also play significant roles. Natural factors like solar radiation and volcanic activity have had minimal impact on global temperatures, emphasizing the dominant influence of human activities. Human activities contribute to climate change by burning fossil fuels, which release CO2 and N2O, deforestation, which reduces CO2, absorption, and livestock farming, which produces methane from digestion. Certain practices like using nitrogen-based fertilizers and emitting fluorinated gases from appliances release potent greenhouse gases that accelerate global warming and impact ecosystems. Reducing carbon dioxide and other greenhouse gas emissions, such as methane, is crucial to slowing climate change, with achieving net zero emissions being key to halting global warming and protecting the environment and human health. Water is a vital resource for life on Earth. Chemically, it is a compound made of two hydrogen atoms and one oxygen atom. However, natural water from rivers, lakes, and oceans usually contains dissolved gases, minerals, and other substances which can influence its properties and suitability for drinking, agriculture, and industrial use. The hydrosphere includes all Earth's water, with oceans covering 71% of the surface and holding 97% of the water. While freshwater accounts for less than 1%, oceans regulate climate and weather, with the Mariana Trench being the deepest point at 10,912 meters. Hydrospheric processes involve the movement of water through its solid, liquid, and gas states, such as evaporation, moisture transport, and water movement through rain, rivers, and oceans. These processes are essential for life on Earth, with groundwater playing a key role in the water cycle. An aquifer is a rock layer that contains water. Below the water table, the aquifer is saturated with water, while above it is the unsaturated zone. Groundwater can be pumped from the aquifer by drilling below the water table. The amount of water that can be extracted depends on the aquifer structure. With limestone storing more than granite, some areas also have underground rivers. Water is vital for life, but human activities negatively affect the water cycle, causing environmental issues. Understanding how humans impact the water cycle is essential for finding solutions to protect and manage water resources sustainably.
What is the water cycle? The water cycle involves the movement of water through evaporation, condensation, precipitation, and flow across land and into plants. Human activities such as pollution, deforestation, and extraction disrupt this natural process, leading to environmental issues like water scarcity and contamination. Understanding these impacts is essential for sustainable water management. How do humans impact the water cycle? Human impact the water cycle both directly through activities like building dams and withdrawing water from lakes and rivers and indirectly by contributing to global warming. Both types of impact disrupt the natural flow of water, leading to potential issues like water shortages and changing weather patterns. Hydroelectricity. Hydroelectricity generates power by converting the gravitational energy of water behind a dam into electricity. While it is a clean energy source, it disrupts the water cycle by altering river flow, blocking fish migration, and affecting aquatic ecosystems. This can lead to imbalances in upstream and downstream water flow, buildup of silt, and reduce water availability for plants and animals. Deforestation. Deforestation disrupts the water cycle by reducing the number of trees that release water vapor into the atmosphere through transpiration. This leads to drier land and air, affecting local humidity levels. It also increases runoff and leaching, which can worsen droughts and flooding. Irrigation. Irrigation supports agriculture by artificially watering land, but it disrupts natural water flow, causing runoff and depleting water from its original source. It can also introduce salt into water systems, impacting water quality and soil health. Climate change. Climate change, driven by human activities like burning fossil fuels, is significantly affecting the Earth's water cycle. Rising temperatures lead to increased evaporation and faster melting of ice sheets such as glaciers. This causes sea levels to rise and disrupts other important processes in the water cycle, potentially altering weather patterns, precipitation, and water availability. How to minimize our impact on the water cycle? Conserving water at home, using public transit or biking instead of driving, minimizing fertilizer use in your garden, avoiding pollution, and using compost are small yet impactful actions. When practiced consistently, they collective they collectively contribute to reducing environmental harm and protecting and promoting sustainability. Earth soil. Soil is crucial layer formed from rock weathering containing minerals, organic matter, air, water, and organisms that support plant growth. Proper soil management is essential to prevent erosion, ensuring food security and environmental stability. Soil layers. Organic is nascent organic matter. Surface, organics mixed with minerals. Subsoil is nascent mixture sand, silt, or clay. Substratum, substratum is nascent parent rock. Then ang bedrock is nascent unweathered parent material. Factors affecting soil formation. Soil forms through physical, chemical, and biological weathering processes, including mechanical breakdown, chemical reactions, and the actions of living organisms. These processes are essential for soil formation, which supports life on Earth.
Soil formation is influenced by five main factors: parent material, living organisms, climate change, topography, and time. These factors interact to create a diverse range of soil across the Earth's surface. Parent materials. Soil minerals are formed from the withering and erosion of parent rocks. Natural processes like wind, water temperature changes, and living organisms contribute to this breakdown. The type of parent rock and the condition during its withering influence the soil's properties, such as fertility and texture. For instance, granite typically forms sandy, infertile soils, while basalt form fertile, clay-rich soils in moist condition. Human activities and earth soil. Soil is crucial for human life, but its misuse can lead to degradation, reducing its ability to function. The Sumerians i- irrigation of desert soils around 3000 BC helped their civilization thrive but eventually lead to soil salinization, which harmed crop production and contribute to their collapse by 2200 BC. Today, salinization, along with contamination, desertification, and erosion, remains a significant challenge to soil health and productivity. Erosion. Erosion is a natural process that shapes the Earth's surface, but human activities like deforestation and overgrazing accelerate it, causing soil loss, environmental degradation, and reduced food production. Desertification. Desertification is the severe degradation of land in arid regions, leading to poor vegetation, desert expansion, and reduced productivity with significant environmental and social impact. Acidification. Soil acidification is a natural process where leaching removes basic cations, lowering pH and increasing acidity. Fertilizer use accelerates this, affecting soil health and ecosystem in all biomes. Deforestation. Deforestation leads to the habitat loss, biodiversity decline, and environmental damage. Sustainable practices and reforestation are key to mitigating its impact. Salinization. Salinization is the buildup of salt in soil, damaging its structure and limiting plant growth, especially in desert and prairie biomes. Mining. Surface mining alters landscape and soil science is essential in reclaiming to restore the land and vegetation to its original state. Green chemistry. Green chemistry aims to reduce or eliminate hazardous substance in chemistry, chemical products and processes, promoting sustainability and safe throughout the product's life cycle.
Green chemistry aims to prevent pollution at the molecular level, reduce environmental and health impact, and design safer chemical products and processes by eliminating hazard from the start. How green chemistry prevent pollution? Green chemistry prevent pollution by eliminating hazardous chemicals at source while remediation and address the cleans up stressing pollution. Green chemistry applies to cleanup technologies that eliminates hazardous substances such as using non-hazardous solvents instead of harmful chemicals, improving environmental and health safety. Green chem- eh, the 12 principles of green chemistry. Green chemistry principles focuses on reducing waste, maximizing material use, minimizing toxicity, and improving safety and green efficiency by designing safer products and using non-harmful solvents. Green chemistry promotes sustainability by using renewable feedstocks, avoiding chemical derivatives that generate waste, and using catalyst instead of stoichiometric rege- reagents to improve efficiency and reduce waste. Green chemistry principles include designing products that safely degrade after use, using real-time monitoring to prevent pollution during production, and minimizing the risk of accidents. Green chemistry of the Pollution Prevent Act of 1990. The Federal Pollution Prevent Act of 1990 establishes the national policy of preventing the reducing pollution at the source whenever possible. Source reducing reduction refers to practices that decrease hazardous substances, pollutants, or contaminants before they enter waste streams or the environment, and also reducing the associated risk. So these are the reference of our report.